Okay, so 48 million trips from here to Obegal. If you somehow made all those trips, you will have gone the same distance as Voyager 1. Okay, so Voyager 1. It was launched September 5th in 1977 on a Titan IIIe rocket. It was made by the Jet Propulsion Lab for about $215 million, and it takes approximately 17 hours for data to go from here to Voyager or from Voyager back here. And it has a thing on it called a golden record, and it's basically what NASA wanted our first contact with any non-human life to be. And so it has images on it, music, sounds of the planet, and greetings in over 55 languages on the spacecraft. All right, here's some background terms of the paper. Before we start, the termination shock, which is seen right here, it's basically a shock wave, or it's like a boundary basically that slows down a solar wind that flows through space, and the boundary that is between the termination shock and just much cooler interstellar plasma is called the heliopause, and it is characterized by very dense plasma. The heliosheath is the space between the termination shock and the heliopause, and the bow shock is also known as a bow wave. It's kind of like the first a boundary between all of this and just like the rest of just space in general. And some background terms from Voyager 1 itself are the teams / the instruments that are on Voyager 1, and they are the MAG team, which investigates magnetic fields that interact with Voyager 1, the LECP team, which characterizes all interactions between low energy charged particles and Voyager 1, the cosmic ray investigation team, and the plasma wave investigation team. And so I'm just going to stop here for any questions anybody has about any of this briefly. Okay, sweet. So my paper is called In Situ Observation of Interstellar Plasma with Voyager 1. And so what my paper is claiming is that Voyager 1 has now entered interstellar space. And so before we go into any data or anything, I want to give you just a brief outline of it. So just a timeline of events are as follows. So first, it was obviously launched in 1977, and in 1983 through 1993, the PWS team found radio emissions from the outer heliosphere, and so that was found to be a really important later, because it was a way to verify that we knew just some things from the heliosphere. And on March 2012, we observed from Earth a solar eruption that pushed plasma towards Voyager 1. This was not seen as a very important at that time, but it becomes a very important much later. And then on July 28th through August 25th, the LECP and CRS teams find a possible encounter with the heliopause. And so what we find is that there's a reduced amount of TSPs, which are termination shock particles, and ACRs, which are anomalous cosmic rays, and those are very prevalent in the heliosheath. And so by seeing a reduced amount of that, we would be in the heliopause. But that actually could never be confirmed as our first push into the heliopause, because the MAG team could not find anything that could verify that, and the PWS team could not verify that there was a change in plasma density. And then on April 9th, 2013 through May 22nd, 2013, there were strong electric field detections. And they had very spiky variations that were characteristic of the electron plasma oscillations. And so let's take a look at that data right now. This is a direct data from Voyager 1. As you can see right here, there's like a spiky reading. And so basically, we are looking at it through a wideband spectrogram, which is a plot of the height or the amplitude of the waves versus like the time in like the days of the year. And so this is very important because if we can find the electron oscillation, we can measure the density of the plasma, because the frequency of the waves is roughly equal to the square root of the density of the plasma in space. So I'm just going to pause here for any questions.
So right now they think they're in the heliopause,
Yes.
and then this is going to confirm it.
Yes.
So like what Alessia was saying, so if you know you're in the heliopause, does that mean you are in interstellar space? Like what would be the interstellar, the bow thing?
Yes, let me go back to that map I had. So basically, we think we are around here, and we're trying to confirm that. And if we can confirm that we're right here, then we'll know that we'll soon be, or like right now, are in this region here, which is past our solar system. So now, oh, sorry.
On the graph there, like the black square bars, and then there's also things that look like the heart rhythm. So what's the difference between the spiky things and the shaded implants?
These are the averages of like the wave heights, and these are the peaks. These are the peaks.
Got
Those
it.
are the averages.
Okay, thank you.
Right. So, what NASA did was to make the data more readable. They put this data through a Fourier analysis, which is basically a way of clearing up or cleaning up any data by like averaging out all of the waveforms. And so what we can see from that is that there's a very narrow bandwidth of like a few percent that we're seeing through these waves, and that's an average of about 2.8 kilohertz. And using that formula that I had mentioned earlier, we can see that we're at a density of 0.08 centimeters cubed of plasma. And we can also see, based on this and some recordings that we have from the Voyager 1 tape recorder, that plasma density is increasing as time goes along. Yes.
Can you go back? So these different letters, these different plots, flip back to the other one. Those are just different times here, right?
Yes.
Up at the top.
They
Oh, okay.
correspond with those.
Okay, cool. Thank you.
Okay, so after that, they basically morphed all of those like small blocks together, and this is kind of like a wide-angle lens, or like the bigger picture of what they saw. So here is a smaller event that they actually could not see in the previous data, but they did see, or hear actually rather, in a in a tape recording found off of a Voyager 1. And here is that large spike that we saw in the past data. And using both those events, they could plot the rate of change in the plasma density. And they found that to be 2.7 hertz per day, which can be confirmed as a increase in the plasma density, which is a characteristic of the heliopause. So now here I'm just gonna play for you the tape recorder that was on a Voyager 1 that actually has both of the events on it. So, based on this, we can see that the plasma density increased between these two events at like this constant density ramp, per se. And so even though we already know that the density has increased, I wanted to make sure that we could confirm it one more time. So we looked at those electric field measurements that we had seen from 1983 through 1993, and we compared them to what we saw when we actually found those spikes. And what we can see here is like a mapping kind of the 1992 through a 1993 event, which was captured during that window, and right here a mapping of the event that we saw in 2012, and if we compare them, and they did here by changing the timeline and just the timeline. The slopes are roughly the same at about a 1.9 kilohertz, and so that gives us some context that that the events that were seen in 1992 were roughly the same density as the events that we saw in 2012. And just to confirm one more time that we were right, because why not? I basically wanted to make sure that we weren't just seeing one ray of plasma that was being shot at like a spacecraft. So they spun a Voyager around like quite literally, and as you can see here, they found data points as the roll kept going on, and they observed that it wasn't just coming from one direction, and that it was coming from all directions. So then, based off of that, they could see that it wasn't just one beam, but it was the entire environment that was being observed. And this is just a picture of Voyager 1, and it was being spun on the z-axis right here, so it was being spun in this direction, basically. Any questions so far?
How'd they get it to spin?
They have like small onboard, like not really like engines kind of, but like they can fire off like a small propellants, basically. So, what this means for us back home. So, it's the farthest that a spacecraft has gone in like the history of mankind, and it was not really like thought to be able to like record data for this long. It has less power on it than like I was gonna average a cell phone. So I mean, it's a pretty remarkable that it's like still recording data from that far away. It would be like the first contact we have if we ever do have contact with any non-human life, and it would be like our first like our a first impression kind of, and it's basically giving us data from a place that humans have not been to and probably will not be able to go to for a very long time, and so that's pretty remarkable. Yeah. So excited. Thank you.
I have two questions. One, do you know anything about Voyager 2? Like, were they launched at the same time?
Voyager 2 was actually launched like 16 days prior to Voyager 1, which doesn't really make sense because it's 2, but it's launched before. Actually, if we go back to this map here, this is where Voyager 2 is right now. It's a bit farther behind because it traveled on like a separate route kind of than Voyager 1, but it is on its way out there still.
And then also, was the goal of Voyager 1 just to go as far as possible?
It was its mission was to observe interstellar space, so it's just basically finally completed this mission.
So, if it wasn't expected to last this long, how was its goal to reach interstellar space?
They
was there a malfunction with the machinery that precluded it from doing so, or something like that?
So it there are a lot of parts of it that don't really work anymore. There's like an actual tool on there that's just like supposed to just find plasma density, but that broke back in like 1980. So there have been like a lot of failures with it, but it's just like it's kind of kept going, and NASA has found a way to find the measurements based off of other instruments.
When is it going to break that heliopause,
It already has.
It already has?
Yeah, it's in interstellar space now.
Okay.
So, you said that its job will end in 2 to 7 years. So is that basically the time it'll take for the rest of the battery or whatever to run out? Or
So basically, it's not expected to function by 2020, which is in 2 years. But the thing is, with space, there's nothing that's really gonna stop it. So it'll keep going forever. So yeah.
If they made something now, would they be able to immediately tell, say they could put something right where Voyager 1 is right now, it would be easy for them to tell, or is it more difficult because it's
what do you mean by
I don't know, could they, would they have technology now to, know immediately if they're in interstellar space?
Well, yes, actually, because there was supposed to be a tool on there that measured plasma density, but that actually failed back in 1980. So, yes.
So has it been getting its power from the sun? Does it have solar panels on it?
It does have solar panels on it, but I'm not sure if they're still functional.
Have they launched anything more recently that it has a similar mission to this?
I don't think there's anything that has a similar mission, but I can get back to you if
I just was curious if because obviously technology has changed dramatically from the 70s. So would they have sent out other things that have more capabilities?
Not to my knowledge. But, yeah. Thank you.